Today on AI Paper Podcast, we are breaking down Self-Distillation Enables Continual Learning by Aydin Schenfeld, Mehul Damani, Jonas Hubater, and Pulkit Agrawal from MIT's Improbable AI Lab and ETH Zurich. Here's the short-form summary for those in a rush. The industry has a major problem. Foundation models are static. To update them or teach them new skills, we pretty much rely on supervised fine-tuning, SFT, because we just don't have explicit reward functions for reinforcement learning. But SFT is inherently off policy, and this causes catastrophic forgetting and, poor generalization because the model is training on a fixed distribution, not its own generations. So the authors introduce SDFT, or Self-Distillation Fine-Tuning. This method leverages the model's own in-context learning capabilities. It uses the model as its own teacher by conditioning it on expert demonstrations, while the student, which is the same model without the demonstration, learns to match that distribution. The results are pretty significant. SDFT achieves on-policy learning without a reward function. It outperforms SFT on spill learning benchmarks, reduces catastrophic forgetting to near zero, and it scales effectively, showing better performance as the model size increases.
It's essentially a way to get the stability of RL using only the data you already have for SFT.
Okay, that's the abstract. But I want to step back and, look at the actual engineering headache here. If I'm building an LLM application today, my biggest fear is updating the model. I want it to learn a new API or a new set of medical protocols. But every time I fine-tune it, I risk giving it a lobotomy where it forgets everything it knew before. Why is this still such a hard problem?
It comes down to a fundamental dilemma in post-training. We're essentially stuck choosing between two imperfect options: reinforcement learning, or RL, and supervised fine-tuning, or SFT.
And theoretically, RL is the gold standard, right? If we could run RL on everything, we would.
In theory, yes, RL is on policy. That means the model generates its own attempts, its own trajectories, and learns from its own mistakes based on feedback. Because it's actively navigating the state space itself, it creates these very robust, stable representations. It knows how to recover when it drifts off track.
But we don't use it for everything because of the reward function problem.
Exactly. If you're training a robot to walk, the reward is easy. Did you fall over? No, plus 1 point. But if you're training a model to write Python code or, say, diagnose a rare disease, there's no mathematical function that can look at a paragraph of text and give it a perfect numerical score.
So we default to option B, which is SFT. We just show the model the correct answer and say, minimize the loss on this text.
We take a data set of expert demonstrations, questions, and perfect answers, and we just force the model to minimize the negative log likelihood of those tokens. It seems reasonable. If you have the right answers, just train on them.
But the authors of this paper argue that SFT is technically flawed for continual learning. They call it off-policy. I want to push on that term a bit. Why does off-policy matter so much if the data is good? I mean, if the expert data is perfect, shouldn't the model just learn to be perfect?
It matters because of covariate shift. This goes way back to research by Ross and others in 2011. Think of it this way. SFT forces the model to mimic an expert's actions, but only in the states the expert visited.
Okay, let's use the classic driving analogy. SFT is like memorizing a race car driver's turn-by-turn directions.
That's the perfect analogy. You memorize the perfect line. Turn left 10 degrees at marker A. But during inference, you are driving the car and you aren't the expert. If you make one tiny mistake, say you drift an inch to the left, you are now in a state the expert never visited. You've never seen the track from this specific angle.
And because I was trained off policy, just watching the expert, I have no idea how to recover.
Right. You drift further off track, the errors compound, and you crash. That is covariate shift.
Whereas if I had learned via RL on policy, I would have driven the car during training, made that mistake, and then learned how to correct it.
Precisely. And the other side effect of SFT's blind memorization is catastrophic forgetting. SFT aggressively updates weights to maximize the probability of the new data set. It doesn't care if it destroys the delicate representations that allowed the model to do math or, reason about history.
It just overwrites them.
It just overwrites them.
So the goal is to get that RL-style stability, where the model learns to drive the car itself, but using only the static data we have for SFT.
And that is where SDFT, Self-Distillation Fine-Tuning, comes in. They managed to create a teacher-student loop using only the model itself.
Okay, walk me through this mechanism. How can a model teach itself something it doesn't know yet? It sounds like pulling yourself up by your own bootstraps.
It relies on something we all know works: in context learning, or ICL. We know for a fact that a pre-trained model gets smarter when you put a demonstration in the prompt. few-shot prompting works.
Right, you give it an example and the output quality just jumps.
So the authors exploit this gap between the zero-shot performance and the few-shot performance. For every single training example, they set up 2 forward passes. First, the teacher. This is the model conditioned on the query, plus the expert demonstration.
So the teacher is effectively cheating. It's looking at the answer key in the prompt.
In a sense, yes. It has the demonstration, the X and the C. Then you have the student. This is the exact same model, same weights, but conditioned only on the query, just the X.
And here's the crucial distinction, because this is where I got a little stuck reading the methodology at first. The student isn't just told to copy the teacher's text, right?
No, and that is the key difference from SFT. If you just copied the text, you'd be right back to square one. Instead, the student generates a response by sampling from its own policy. The student rolls out a trajectory.
So the student is driving the car.
Yes, student drives. Then the loss function minimizes the reverse KL divergence between the student's distribution and the teacher's distribution.
Hold on, let's pause on reverse KL divergence. Is that just a technical implementation detail, or does it actually change the behavior? Why not just standard KL?
It fundamentally changes the behavior. Standard forward KL, which is what ST kind of approximates, tries to cover the entire distribution of the target. It's mean seeking. It tries to average everything out. Reverse KL is mode seeking. It effectively forces a student to focus on the high probability regions, the peaks of the teacher's distribution.
So it encourages the student to be decisive and precise where the teacher is confident, rather than trying to hedge its bets across everything.
Exactly. But the magic isn't just the loss function. It's the fact that the student is generating the text itself. It's getting a gradient signal saying, hey, your probability distribution for this token didn't match the version of you that saw the example. The student's learning to navigate the state space itself, correcting its own rollout to match the wiser version of itself.
This sounds suspiciously like inverse reinforcement learning, IRL.
It is mathematically equivalent. The authors actually provide a proof that this self-distillation objective maximizes an implicit reward function. Usually, IRL is a nightmare to run. You try to infer a reward function from data, which is unstable, and then you run RL on top of that. It's computationally very expensive.
But SDFT bypasses the explicit reward modeling.
Completely. They posit an in-context assumption. They basically assume that the model conditioned on a demonstration approximates the optimal policy.
That feels like a pretty bold assumption, though. Is a model with a prompt really that much better than one without, enough to act as a ground truth teacher?
Well, they validated it empirically, to be sure. They looked at the 2 alpaca benchmark. The base model success rate was about 42%.
Okay.
But when they ran the teacher mode, prompting it with a demonstration success, hit 100%.
Wow. Okay, so in this case, the teacher really is an expert relative to the student.
Yes. But there's a second, more subtle benefit that helps with the forgetting problem. The teacher's distribution is structurally much closer to the base model than an SFT target is. They measured the KL divergence. The teacher stays within a trust region of the original weights.
I see. Because the teacher is just the base model plus a prompt, it hasn't drifted that far in latent space. So when the student aligns with the teacher, it's staying closer to home.
Exactly. SFT yanks the weights aggressively toward the new data. The teacher gently guides the student while staying close to the original representation. It prevents that lobotomy effect we often see with aggressive fine-tuning.
Okay, let's look at the scoreboard. They tested this on skill learning and knowledge acquisition. I know they used a Pareto frontier to visualize the trade-offs, which is always nice to see.
The Pareto frontier is really the best way to see this. On the x-axis, you have accuracy on the new task, let's say medical reasoning. On the y-axis, you have performance on prior benchmarks like HELISWAG and MMLU. With SFT, you see a steep drop-off. As it learns the medical task, its general reasoning capability just falls off a cliff.
The classic trade-off. To get good at medicine, I have to forget history.
Right. But with SDFT, the curve moves to the right and stays high. It achieves higher accuracy on the new task than SFT, while maintaining near baseline performance on the prior tasks.
They also did a sequential stress test, right? Training on science, then tool use, then medical, one after another.
This is where SFT typically fails, the whack-a-mole problem. You learn medical, you forget science, you relearn science, you forget tools. SDFT, however, accumulated all 3 skills successfully, just kept stacking them.
I want to pivot to the knowledge acquisition experiment, because this is where I think the difference between memorizing and learning becomes really clear. They created a data set of fake future events?
Yes, the 2025 Natural Disasters dataset. They generated Wikipedia-style articles about fictional events, like a 2025 Myanmar earthquake. Since the base model has a knowledge cutoff, it couldn't possibly know these facts.
So they tried to teach the model these new facts. How do the different methods compare?
Well, standard continual pre-training, or CPT, failed miserably, single-digit accuracy. It just couldn't integrate the specific facts effectively from that small amount of data. SFT did okay on strict accuracy, hitting 80%. SDFT hit 89%.
But the real kicker wasn't just regurgitating the facts. It was the out-of-distribution generalization.
Right. They tested on indirect questions. These are questions that require the knowledge but don't ask for it directly. So instead of what happened in Myanmar in 2025, it might ask a question where the answer depends on knowing about the earthquake.
Like, did the GDP of Southeast Asia drop in 2025 due to seismic activity?
Exactly that. And SFT struggled there. It fell apart. But SDFT achieved near-perfect accuracy, 98%. It actually matched an Oracle RAG system that had access to the text during inference.
That is wild. That suggests SFT just memorized the string of text. It didn't update its world model. SDFT actually integrated the fact that the earthquake happened and could reason about its consequences.
It implies a much deeper level of internalization. The reasoning was distilled, not just the token sequence.
Now, I want to spend a moment on what I think is the most, the biggest aha moment of this entire paper. If you take one thing away, it should be the experiment involving the reasoning model. OLMO 37B Think.
This is a fascinating result. The problem they were addressing is that most training data sets, they just give you the answer. Don't show the work. They lack the chain of thought, or CODI.
And we know that if you fine-tune a reasoning model, one of those models that likes to pause and think on answer-only data, you usually damage it.
Cobotomize is the word often used. If the model sees thousands of examples of short, direct answers, it learns that the probability of generating a thinking token is low. It collapses into short, shallow responses. In their test, SFT actually dropped accuracy from 31% down to 23%. The model stopped thinking.
But SDFT fixed this using the exact same data. How? If the data doesn't have the thinking in it, where did it come from?
It came from the teacher. Even though the dataset only had the answer, the teacher was conditioned on that answer and the prompt. And because the base model has strong in-context learning, the teacher internally generated the intermediate reasoning traces, the chain of thought, to bridge the gap between prompt and answer.
Wait, so the teacher is thinking in the background, implicit reasoning, to verify the answer it was given?
Effectively, yes. The teacher assigns high probability to the reasoning path that leads to the correct answer. The student, in trying to match the teacher's distribution, distills that entire thinking process.
So the student learned to think just by watching the teacher get the right answer?
Yes. Accuracy jumped to 43.7%, and crucially, the token count, the length of the response, remained high. It didn't collapse into those short answers.
That is huge. It implies you can use SDFT to fine-tune reasoning models using standard, cheap, non-reasoning datasets without breaking their reasoning capabilities.
It essentially allows you to bootstrap chain of thought data from the model itself, removing the bottleneck of needing expensive human annotations.
Yeah.
You get the reasoning for free, hidden inside the model's own capability.
Okay, this all sounds great. I'm ready to fire up the cluster. But let's talk engineering reality. There's no free lunch. What's the catch?
The catch is compute. You are generating samples during training. The paper estimates it's about 2.5 times the FLOPs and 4 times the wall clock time compared to standard SFT.
4 times slower. That's a hard sell for a lot of teams. If my training run takes a week, I don't want it to take a month.
It sounds bad, but you have to look at the total pipeline cost. Right now, to fix the forgetting caused by SFT, engineers run these complex multi-stage pipelines. You do SFT, then you realize it forgot something, so you do a re-invoking stage or repair stage where you mix in old data and train again.
True. The amount of time I spent fixing the damage SFT did is non-trivial.
Exactly. SDFT is actually cheaper and faster than those complex multi-stage pipelines while performing better. So it's slower per step, but it might save you from running 3 different distinct training runs just to fix the mess you made.
Efficiency in the macro sense. Okay. Are there limits on the model size?
Yes, scaling laws definitely apply here. SDFT relies entirely on the model being smart enough to be a good teacher. When they tried this on a 3B model, SDFT actually performed worse than SFT.
The teacher was too dumb to provide a good signal.
Essentially, the 3B model couldn't extract enough signal from the demonstration to be a useful guide. But at 7B and 14B, SDFT significantly outperformed. The gap widens as the mile gets bigger.
One implementation detail mentioned was the teacher weights. You can't just use the live student weights for the teacher, right? That sounds like an instability waiting to happen.
Right? That creates a feedback loop that leads to collapse. If the student is just chasing its own tail, it learns nothing. But you also can't use a frozen base model because it's too static. It doesn't adapt as the student learns. They used an EMA, an exponential moving average of the student weights.
So the teacher is a slightly lagged, smoother version of the student.
It provides a stable, wiser moving target that evolves along with the training, but smooths out the noise. This is pretty standard in self-supervised learning, things like BIOL or Dino, but applied here to language modeling.
Before we wrap up, I want to touch on the learned artifacts mentioned in the discussion. This was a quirky side effect that I found hilarious.
This was amusing because the teacher is prompted with phrases like, here is an example, and the student learns to match the teacher's distribution. The students sometimes learn to output meta-commentary.
Like starting a sentence with, based on the example above, even when there was no example in its own context.
Right. The student was hallucinating the context because it was distilled from a context-aware teacher. It learned the syntax of the interaction. They fix this with masking, just ignoring the loss on the first few tokens, but it highlights just how powerful the distillation is.
It raises a provocative question to end on. If the student is learning to hallucinate a context that helps it answer better, are we sort of redefining what hallucination is?
It's a deep question. The teacher's thought process relies on the demo. The student doesn't have the demo, so it simulates the state of having seen one. Technically, that's a hallucination relative to the student's input.
So perhaps as models get better at self-distilling, we aren't just compressing knowledge. We might be witnessing the first steps of models effectively meditating on their own potential futures, hallucinating a context to better ground their answers. Is hallucination actually a necessary intermediate step for internalization?
If it works, maybe it's not a bug, but a feature of learning.
Something to think about. That's it for this breakdown of self-distillation fine-tuning. We'll catch you on the next one.